This video is going to show you how to do the Lewis dot diagrams for ionic bonding. So this first section is going to help you be able to visualize what's happening to the electrons as these atoms participate in the ionic bonding. And before you can actually show the Lewis dot diagrams, you have to draw the dots. So these dots are the valence electrons. Hopefully you can look at the periodic table and identify how many valence electrons each element has. So magnesium has 2, oxygen has 6, and the magic number for chemistry is 8. This is called the octet rule, and when elements have 8 valence electrons, that means 8 electrons in the outer shell, they're particularly stable. So for oxygen, it already has 6, it just needs to gain 2 more. For magnesium, it has 2, and it's really hard to gain 6. That's a lot of valence electrons. So what magnesium would rather do is donate those 2, because once that shell is gone, the next shell is its valence shell, and now it will have 8. So if it's below 4 valence electrons, they're more likely to lose the electrons, and if it's greater than 4, they're more likely to gain. So in this case, magnesium is going to donate its 2 electrons to oxygen. We can put one right there, and we can put one right there. So now magnesium, we're going to show it without any valence electrons, even though it really does have some valence electrons in the next shell. And it looks like this, and now oxygen is stable. And in the process, magnesium has become a positive 2 because it lost 2 electrons. Oxygen has become a negative 2 because it gained 2. And now they're attracted to each other because of those opposite charges. And when we write them, we don't actually put the charges on them in the final answer, but those charges will be important in the next section that I'm going to show you. All right, let's do another one because they're not all that simple. Calcium has 2 valence electrons and bromine has 7. So calcium can lose one of its electrons to bromine, but the problem is now bromine has 8 and it's full, and calcium still has that other electron to lose. So in this case, we need another nonmetal, another bromine, to receive that last electron. So now calcium has become a positive 2 because it lost 2 electrons. Each bromine is negative 1, so you write it based on the number of electrons gained or lost per atom, and so each bromine only gained 1 electron. But we have 2 bromines, and so we're going to show that with a subscript down here to show that we have 2 bromines. So in the final answer, again, we don't put the charges, even though that's what's holding them together, and then we're going to put the subscripts to show how many we have. Let's do one more together, and then I'll let you try some by yourself. So this one, sodium has 1 valence electron. Sulfur has 8. So we're going to say 4, and then come back for, I'm sorry, I said 8, I meant 6. Come back for 2 more. So sodium can donate 1 of its electrons to sulfur, and now sodium is good. It lost the 1 that it needed to lose. But sulfur now has 7, and that's not okay. It needs to have 8. So we need another sodium so that now sulfur has all 8. Be careful when you're writing these. I didn't mention this before, but make sure you always put the positive element first. So the thing that lost electron needs to be written first. So sodium is first, and each sodium lost 1 valence electron, but we do have 2 of them. So we're going to put 2 down here. And then sulfur has all 8. Forgot to draw the ones on bromine. These should all have 8 too. And sulfur is now a negative 2 because it has received 2 electrons. And again, we don't put the charges on the final answer, but we do put those little subscripts. So you have several more in your notes if you didn't do those already. I want you to try them yourself first and then check this video and see if you got them right. So for now, go ahead and pause this video and do these in your notes and then check. All right, check your answers for these and notice especially the subscripts. So the first one that you did by yourself was KF, and that's a perfect relationship. K loses 1, F gains 1, so you don't need any subscripts. For Mg and I, you needed 2 iodines to match the magnesium. BES, you didn't need any extras. But NaO, you needed an extra sodium to donate 1 more electron to the oxygen. And then that last one, you needed 3 bromines to match up to the aluminum. Now, here's the thing. What we really care about is being able to write these formulas over here. However, scientists are not going to sit there and draw arrows and dots all over their papers. So there's an easier way to do it than drawing that. We teach it that way so you can visualize what's actually happening with the electrons, but now I'm going to teach you something called crossing your charges. And the point of this is to reach a net charge of 0. Net means overall. So for all of these, they need to add up to 0 in terms of their charges. For this, instead of using valence electrons, we're going to use oxidation numbers. And these are the charges that things tend to become. So sodium has 1 valence electron, which means it's likely to lose that valence electron and become a +1 charge. Sulfur has 6 valence electrons, so it's likely to gain 2 and become a -2 charge. Now, +1 and -2 do not equal 0, and so we're not quite finished with this one. What we're going to do, the easiest way to make it 0, is to take the number from sodium and bring it down to sulfur, and take the number from sulfur and bring it down to sodium. Once the numbers come down, they're no longer charges. Now they're telling you how many you have. So the 2 came down from sulfur and the 1 came down from sodium, and we don't really write 1, so you can just leave it as S. And so now we know that the formula is going to be Na2S. Let's do another one. If you look up the oxidation number for magnesium, it's +2, and bromine is -1. So again, we're going to take this number and bring it down to bromine. We're going to take this number and bring it down to magnesium. So Mg has a 1 on it, and bromine has a 2. This is going to be so important for the next 2 or 3 chapters, because if you forget to cross those charges down, you're going to have trouble balancing a reaction. And if you can't balance a reaction, you're going to have trouble doing calculations. So it's kind of going to build on itself. This is the first step in a series of lessons that you're going to learn. So pay close attention to this. If you're having some trouble, just let me know in the live session. Let's do one more together, and then I'll let you try the last ones by yourself. So actually, we'll do a couple more. Strontium is +2. Oxygen is -2. So now when you cross these down, you get a 2 down here and a 2 down here. And the last step for crossing charges is that if you can simplify, you should. So a 2 to 2 ratio, that's really what this is, that can be simplified to just a 1 to 1 ratio. Notice that these two already add up to 0, +2 and -2 already add up to 0. So you don't really need to cross anything down there. And the next one, we'll do one more together. Gallium is +3. And nitrogen is -3, so again, notice that they already cancel out. So we don't need to do anything there because they already add up to 0. All right, take a few minutes and try those last 4 by yourself and then check your answers. All right, go ahead and check your answers for these, so see if your subscripts are correct. And I wanted to do this last one because it's probably the trickiest. So the first thing is oxygen you can look up as a -2 charge. And then there's germanium, which is in the +4, -4 column. And so you're probably thinking, well, how do you know which one it is? And the answer is that it's always going to be the opposite charge of what it's bonded to, because opposites attract. So instead of being -4, then you would have 2 negatives together. This is going to be +4. Then we're going to take that 2, bring it down to germanium, take that 4 and bring it down to oxygen. And then remember, the last step is if you can simplify, you have to. So 2 and 4 can be simplified to just 1 and 2. And so the final answer is GeO2. And that is it for ionic bonding Lewis structures.